Welcome to Lab 101. Go ahead and grab a stool. I am absolutely thrilled to be your guide for today's explainer. Now, as a science professor, there is really one crucial lesson I insist every single student masters before they even think about lighting up a Bunsen burner. Today, we are talking about the absolute fundamental recipes of science. Because, look, before we can unravel the secrets of the universe, we've got to make sure we're all speaking the exact same language when we measure it. Let's step out of the lab for a second and head into the kitchen. Imagine you're trying to share your absolute favorite award-winning chocolate cake recipe with a buddy on the other side of the planet. You tell them, hey, just use 1 cup of flour. But what if their idea of a cup is some giant oversized coffee mug and yours is a tiny little teacup? It'd be a total culinary disaster, right? You'd end up baking a brick. Well, believe it or not, for a really long time, the scientific community struggled with this exact same problem. Different countries, sometimes even neighboring towns, had totally different sizes and standards for measuring things. Trying to share scientific recipes or experiment results was, quite frankly, just pure chaos. That measurement chaos actually plagued science for centuries. But the big turning point finally arrived in 1961. That's when the International Committee on Weights and Measures stepped in to standardize the whole shebang. They realized that if scientists were ever going to actually collaborate, share data, and build on each other's work without repeating that bad cake disaster, they desperately needed a single, universally agreed-upon system of measurement. And that brings us to the ultimate scientific cookbook, the International System of Units, which we all abbreviate as SI. Now, the absolute key takeaway here is that using SI measurements is what allows scientists everywhere to share and compare their observations seamlessly. It's a system built on 7 base units, and their values are strictly fixed to international standards. So no more guessing, no more weirdly sized coffee mugs, just pure, precise, standardized communication. Now that we've got our universal cookbook, let's flip open the first chapter. Section 1, the 7 base ingredients. What's super interesting about these 7 physical quantities is that they are the raw, fundamental ingredients of the entire universe. Take a look at this list. We've got length measured in meters, mass in kilograms, time in seconds, temperature in Kelvin, electric current in amperes, intensity of light in candelas, and amount of substance in moles. Now, our source material lays down a very strict rule here. These base units cannot be derived from one another, and they cannot be broken down into anything more basic. You literally can't mix time and temperature to bake a meter. They stand entirely on their own. They are the foundational pillars that every single other measurement is built upon.
Which leads us perfectly into Section 2, Recipes for Derived Units. Because let's be honest, science isn't just about measuring isolated things. Once you've got your base ingredients, well, you start cooking. Derived units are exactly what they sound like. They're derived or created by mathematically combining those base units we just looked at. If the base units are your flour, sugar, and eggs, derived units are the cakes, cookies, and pastries you end up baking. We use them to measure way more complex physical quantities, things like speed, area, volume, force, pressure, and electric charge. This comparison really hits the nail on the head. Let's look at the math just like we'd look at a recipe card. In baking, mixing flour and eggs gives you a cake. In the lab, multiplying length by breadth gives you area. Since both length and breadth are fundamentally just measuring distance, you're actually taking a base unit, the meter, and multiplying it by another base unit, a meter. Meter times meter equals a square meter, or m squared. By multiplying 2 super simple base ingredients, boom, we've just baked a brand new derived unit. Let's check out a few more of these baked goods in our derived units table. Look at volume right there. That's cubic meters, which is just 3 length units multiplied together. But it gets even cooler when we mix entirely different base ingredients. Take speed, for example. The recipe for speed is distance divided by time. So, you take the base unit for distance, the meter, and you divide it by the base unit for time, the second. And voila, your derived unit is meters per second. Now, some of these complex recipes actually get their own special names just to save us time, like force being measured in newtons or pressure in pascals. But don't let the fancy names fool you. Underneath it all, they're just perfectly measured combinations of our 7 basic SI ingredients. All right, moving on to Section 3, Scaling Up with Prefixes. Okay, class. So we have our ingredients, and we know exactly how to mix them. But we've got one final lab challenge to tackle. Imagine trying to write out a recipe to bake 50 million cupcakes. Having to physically write out a 50 followed by 6 zeros over and over again?
It's not just tedious. It leaves a massive amount of room for someone to accidentally drop a zero and completely ruin the whole batch. And in science, we deal with the astronomically huge, like the distance between entire galaxies, and the microscopically tiny, like the width of a human hair. The beauty of the SI system is that it's a decimal system, meaning it plays perfectly with powers of 10. So to save us from drowning in an endless sea of zeros, scientists use SI prefixes. These are special little words or symbols we slap right onto the front of our unit to tell us exactly how much we need to scale it up or down.
Let's take a look at how this builds up our scientific vocabulary. Looking at this prefix table right from our notes, if we want to express a huge number, a prefix like mega means 1 million, or 10 to the power of 6. Giga means 1 billion. So instead of writing out a gigantic string of zeros for, say, watts of power, we can just casually write gigawatts. And on the flip side, we have submultiples for the tiny stuff. 1,000th of a meter is beautifully and conveniently expressed as a millimeter. So the thickness of a wire goes in millimeters, while the distance to the next town goes in kilometers. It just makes perfect sense. Let's actually do a quick practical lab conversion together right now, just so you can see how incredibly straightforward this math really is. Step 1, let's say we start with 5,000 millimeters of wire. Step 2, we glance at our table and see that the prefix milli represents 1,000th. So to convert this back to our standard base unit of meters, we just divide our number by 1,000. Step 3, 5,000 divided by 1,000 gives us a nice, clean, easy-to-read 5 meters. This powers of 10 system really makes scaling our recipes an absolute breeze. Now, before we wrap up Lab 101 for the day, I want to reward your excellent attention with a quirky little piece of trivia pulled straight from the margins of our source material. Did you know that the kilogram is literally the only base unit that already has a prefix built right into its name? Think about it for a second. Kilo is a prefix meaning 1,000. But the actual base unit is the kilogram, not the gram. It's just a fascinating little historical quirk in an otherwise perfectly ordered system. So what's the big takeaway from all this? Well, everything from the GPS routing you to the grocery store to the incredibly complex rovers we land on Mars operates entirely on the assumption that a meter is a meter and a second is a second, no matter who is doing the math.